Hello everyone. My name is Vineeth Krishna, and my poster is on a recent paper that we put out in November. It's titled Multi-invariants and Bulk Replica Symmetry. And the paper was with my collaborators Abhijit and Jonathan. So the main goal of this project is to identify and classify measures of multipartite entanglement that admit a convenient geometric dual description when evaluated on holographic states. And the assumptions that we have in this project are that we will be considering entanglement measures, which are called multi-invariants. So these are basically local unitary invariants with a given replica symmetry that acts freely and transitively on the set of replicas. And we will further restrict our analysis to 2D CFTs. And we do have some comments for higher dimensional CFTs, but please refer the paper for that. And we'll further restrict to vacuum state to do some explicit computations, but our ideas are more general and they can be extended to more general holographic states. And I mentioned the word convenient in the goal. So what we mean by convenient entanglement measure is that we want the orbifolded boundary geometry to go back to the original boundary so that the holographic dual can be represented in the original bulk geometry. And the other condition that we require is that the replica symmetry, which is enjoyed by the boundary geometry, to be preserved in the bulk. Now, let's directly go to the final results of our work. So the first result that we have is that we identified and classified the set of all polynomial multi-invariants for which the dual bulk geometry preserves the replica symmetry of the measure for any general configurations of the regions. These are basically the multi-invariants whose extended replica symmetry group is one of the finite Coxeter groups. The other main result that we have in the paper is that orbifolding the bulk geometry, the bulk solution with the replica symmetry will give us a bulk geometry with a tree of conical singularities, which will in general look like this. And our approach identifies infinitely many and infinitely large families of multi-invariants such that each multi-invariant in a given family evaluates identically on a holographic state. So these quantities can in general be used to diagnose if there is a holographic nature of entanglement in a given quantum state. And finally, we have in certain cases, particularly when the replicated manifold is a sphere, we performed an explicit computation of the multi-invariant in the boundary CFT and matched it with the prediction from the bulk geometry. Coxeter groups, these play a central role in our work, and these are basically generated by a set of reflections. Q of, let's say we have a Q-partite measure. In that case, we'll consider Q reflections. And they are defined by a Coxeter matrix Mij, where I and J run from 1 to Q. So the definition of a Coxeter group is as follows. So it is generated by Q generators up to the following relation. One should notice that not all Mijs, the Coxeter matrices, define a finite group. In general, it could be an infinite group. And the finite Coxeter groups are classified based on the following Dinkin diagrams. And the way to understand and the way to read these diagrams is that each node here corresponds to a generator Ri, and two nodes are connected by an edge if Mij, the corresponding matrix element, is greater or equal to 3. And the edges are labeled by the number if the value is greater or equal to 4.